We've been talking for the last few days about objects that are charged, positively charged or negatively charged. We know that positively charged objects are objects that have more protons than electrons, and negatively charged objects have more electrons than protons. But how do they get that way? We talked a little bit about yesterday about how they get that way. We said there's basically two ways of charging objects. One is called conduction, and one is called induction. You guys remember the difference between conduction and induction? One of them is the always way, and one of them is the never way. Connor? Good. So conduction always involves a charge transfer. Q, by the way, is the symbol for charge. C is the unit for charge, just like E is the symbol for energy, and J is the unit for energy, right? Q is the symbol. So we're going to say there's always a Q transfer or always a charge transfer involved in conduction every single time. Induction, there is never a charge transfer, right? So always a charge transfer versus never a charge transfer. What's the other one, Connor? Good. When you've got conduction, it doesn't always involve touching each other or contact, but it usually involves contact. Versus induction, which never involves contact. So if two things touch each other, you know that it's going to be conduction. If two things don't touch each other, then it could be conduction or it could be induction. It depends upon whether charge is being transferred or not. Now we have two subcategories of charging by conduction. Sometimes we don't even talk about the subcategories. Sometimes we just kind of lump them together as one. First subcategory is charging by friction. You rub two things together, they both become charged. One becomes more negative and the other becomes less negative. If I take a piece of plastic here, this is a piece of, it's called a golf tube. It's somebody, you buy them at Canadian Tire or a golf store and you put them inside your golf bag and it keeps your clubs organized. They don't get all tangled up down there, all messed up. This is a piece of a dead rabbit. And when I rub the dead rabbit on the golf tube, you can see, well, you can hear that it's going to become charged. Listen. Can you hear the static? And, how do we know for sure that it has in fact become charged? Because we bring this charged object nearby this neutral object, and we see the charged objects. We know that charged objects attract neutral objects.
And Mr. Dickie, there's a piece of dead rabbit that attached to the
it was sorry? Just stick into it?
It's not happening. You must on my own eyes.
Doesn't want to go there. There.
Oh, we should have a race. You can
so we know this has become charged, guys, and it's become charged by friction. The other way we charge objects by conduction, that is by contact. And sometimes we just call charging by contact conduction. Sometimes we don't differentiate between the subcategory and the category. What do we mean by charging by contact or by conduction? Well, in the end here, all we're doing in that case is just touching two things together. You've got one thing that has a charge of +5, another thing that has a charge of +7. Touch them together, they balance out to be +6 and +6. Now, they're both governed by the law of conservation of charge, which says that charge can't be created or destroyed. It's transferred, it can move around, but you can't create electrons or destroy electrons. So in other words, when we rub two things together, if we had 0 charge total because each one was neutral before I rubbed them together, one of them becomes +5, the other has to become -5 to balance that out. If I had two things that were +10 and +20, touch them together, they're going to balance out, and touch them together, they're going to balance out to be +15 and +15. In either case, the total charge has to remain the same. Now, the other way of charging objects is by induction. Clearly, in both of these cases, we have a transfer of charge taking place. In induction, we do not have a charge transfer taking place. I've got a picture here, much like yesterday's picture, but there's going to be, in a little bit, there's going to be one difference here. Neutral object, we're going to bring a negatively charged object nearby. Tell me what happens to the protons in that neutral object. They stay where they are. what's going to happen to the electrons in that neutral object, Jesse? Yeah, they're going to be pushed away. They're repelled by this negatively charged object. Doesn't mean that all of them go to the left side, but certainly you get a preponderance of them going to the left side, meaning that although it's still a neutral object, still 4 positives and 4 negatives, the one side is negative and the one side has a net positive charge. What do you notice about the side of the neutral object that is closest to the charging object? What do you notice about this side versus this charging object here? Matt? What do you notice about this positive side versus this negative object? They're opposites, right? So that means they're going to attract. This negative object will attract this neutral object because the side that's closest to it is positive, and positive is attracted to negative. So really, that third law that we talked about over the last couple of days, charged objects attract neutral objects, really just happens as a result of positive and negative attracting each other. It's not what I'd call a fundamental law. It happens because of something else. All right. How do I make it permanent? I'm sorry? Attach a ground wire to it? Doesn't matter where we attach that ground wire to, right? Bottom, top, left, right, doesn't matter. One of the down here, doesn't matter where it is. In the end, these negatives, regardless of where they are going to be pushed down into the ground, leaving the ground negative, and the ball here that was neutral becomes positive. Now, really, how much does the Earth become negative as a result of this? The reason the Earth works so well here as something you can ground something else to is because it's so big. It can take essentially an infinite number of electrons, take them, and it can give up an infinite number of electrons almost as well if it needs to. So we say it's an infinite source or sink of electrons. Basically, we don't have to worry about the charge of the Earth. It's so big that no matter what we do to it, it's not going to change it dramatically. What happens if we have that neutral object again, but this time we bring a positively charged object nearby? Let's put the positively charged object down here, though. What's going to happen to the protons? Stay where they are. What's going to happen to the electrons? Yeah, they're going to move towards it, right? They're going to get pulled down here. So now these, we might have one electron still up there, but the net effect is that one side is now negative and one side is positive. What do you notice about the negative side versus the positive side? Yeah, these negatives are attracted to the positives. Charged objects attract neutral objects because positive attracts negative. How do we make it permanent? How do we make it permanent here? The last time we attached a ground wire. Same thing here. Where do we attach the ground wire to? Doesn't matter. In fact, it doesn't even matter if we literally attach a ground wire. We can attach something that's like a ground wire, like, I don't know, some other big object. A big purple egg. If it's a big enough purple egg, then it can give up electrons and go into there, just like the Earth would give up electrons and go into there. Right? Now, how do we make it permanent? We just break the contact. Essentially, it's the same as cutting the ground wire. So you use the Earth attached via a ground wire, or you use something that's big like the Earth that can provide you with a sink or a source of electrons like the Earth. We still call it grounding, and it's the exact same process, it's the exact same phenomenon. It's just that we're not using literally the Earth to do it. All right? Question? No, that's a good question though. Is there a minimum for how big an object should be? It would depend upon the situation. Depends upon how much charge is present and how good of a conductor it is, all kinds of different things. Basically, unless it's pretty small, it's going to serve essentially that effect. So if something like that happens, you don't need to worry about how big it is. It's going to do that. Okay, and the questions that you're going to get at least. All right. Got a couple examples for you here, a couple applications for you. We told you about the fridge stove thing yesterday. You guys sometimes say, well, where am I going to get a real life application for physics? Well, I'll tell you what, if you ever touch a fridge and a stove and you get shocked, okay, then you're going to be pretty happy you learned about electrostatics, right? But you know what? You're also going to be happy you learned about electrostatics if you ever have to deal with it's called an electrostatic air precipitator. It's basically an air filter. You guys know that in your furnace, there's an air filter. Every 2-3 months, you're supposed to replace that air filter. What happens is the air gets blown through this air filter, and it mechanically separates dirt and dust and pollutants from the air, and then the cleaner air keeps going through the furnace, gets warmed up, and then gets blown through the rest of your house. Now, it's not perfect. Particles get through it because it's just literally a mechanical filter, but it helps. I mean, your house is going to be a lot cleaner as a result of having that filter than it would otherwise be. This works better. This works better because it's not based on the size of the particles. You don't have to worry that the particles are too small. They might make it through the filter. This works on principles of electricity. You can see down at the bottom here we have a battery, or a power supply of some sort. There's a positive terminal of the battery and a negative. The positive terminal of the battery will always be the long side of the battery, and the negative terminal will always be the shorter side. Because of that, these red plates become positively charged. And because of that, these blue rods become negatively charged. This is the air that gets blown through by a fan through this apparatus. This air consists of oxygen molecules and nitrogen molecules and all kinds of other different kinds of molecules, but it also consists of small particulates, small particles, dust particles, other pollutants. Some of those dust particles could be filtered out by a mechanical filter, but some of them would be too small. So here's what we do with this electrostatic air precipitator. We send these air molecules along with these dust particles or pollutants. We blow them through this apparatus just by a fan. They're neutrally charged. But then when these things come into contact with these negatively charged rods, what happens to them? The neutral dust particles become negative. How do they become negative? When neutral touches negative, they try to balance out, right? That's called charging by conduction, specifically charging by contact, right? Now, the reality is a dust particle is not going to balance out with this negatively charged rod, right? But you know it is going to gain negative charge, and they're both going to end up being negatively charged. So now you got the air going through that's neutral, but these dust particles and pollutants that are made contact with these blue negative rods, they're now negatively charged. As they get blown through even further, what happens? What happens is these negative dust particles get blown through these red positive plates. Go ahead. Yeah, they get attracted towards it, right? Positive attracts negative well. So these negatively charged dust particles get pulled towards this positively charged plate. They attract to it and they stick to it. What happens to the air molecules? Well, they just keep going through. But they're clean now because they don't have all this dust and pollutants that they had when it went into it. So now you got clean air coming out the other side, and it's not dependent upon the size of the particles being bigger than the size of the openings in the filter. Does that make sense? Clean air. Here's another application of it. This is called electrostatic painting. You'll see this maybe painting cars, painting sometimes metal fences. Generally tends to be painting things that are made out of metal, painting conductors. This is my backyard, or the backyard that I plan to have after Wednesday when I win 649. This is going to be my backyard. So this thing, this gun that sprays the paint consists of a charged rod inside. And that rod could be negatively charged or positively charged. It doesn't really matter. It just means that electrons will go the opposite way if it's oppositely charged. Not a big deal. This paint gun is attached to this tube, which goes to your paint can or whatever it is that contains the paint. And it gets pumped by an air compressor through the paint gun. Right? I mean, see paint guns like this all the time, except that they usually don't have this rod inside that's charged. This rod causes the little droplets of paint that are going through here to become charged. Neutral paint particles become negative by conduction because they're touching and they transfer charge. Now, if this happened to be a positive rod, then these neutral paint particles would become positive by conduction. We get the exact same effect, except the particles would be positive instead of negative. Now, you got these paint particles going through here. They leave the nozzle and they spray out everywhere, right? I got the fence in my backyard on Thursday that I want to paint because there's a couple scratches in it. And not good enough for me. I want a nice, perfect fence. And I decided I'm going to use a paintbrush, but then I said, no, that's going to leave it streaky and it's going to take too long. So I'm going to use a paint nozzle, but that's going to keep spray everywhere. Spray's going to go everywhere, right? And make a big mess of my nice green grass and my pool deck and my pool, and might even go into the ocean behind my house back here and kill the fish. So what I decided to do is use this electrostatic painter, not because it sprays any better than a regular air compressor or an air painter, but because the paint that comes out the other end is charged negatively or positively. Why does that matter? Well, because this metal fence, this conducting fence that is attached to the ground, right, that's already attached to the ground, attracts these negative particles. So negative particles of paint get literally attracted to the fence. That allows for a couple of things. Number one, you get more even coverage. You get more even coverage because paint particles, even ones that are going past and miss the metal fence, get attracted and come back here and coat the back of the fence. You can stand on one side of the fence and partially paint the back of the fence because of the electrostatic force of attraction. Now, the other benefit of this electrostatic painting, not just the fact that you're going to get more even coverage, but you're going to get way less mess, right? Because all this paint that's missing the metal, a lot of it is getting attracted towards the back of it and attaches to it. Make sense? Now, it's negatively charged, but that's okay because this metal is attached to the ground. Right? So you're not going to keep a negative charge on this fence because it's attached to the ground. It's grounded. All right, I want to do a question here. There's a couple of them actually from your worksheet book. It's question number 37 and 38 related to this thundercloud that's going to strike lightning here any moment. All right, so what's going on in this question here? There's a cloud, a thundercloud that's, you see it becomes negatively charged at the bottom. You see that it's actually positively charged at the top? The thundercloud still appears to be neutral, but there's a separation of charge such that the part of the cloud that's closest to the ground is negative. That's the part we care about, the part that's closest to the ground. What does that do to the ground? Well, it says the bottom of the thundercloud usually becomes negatively charged. Before lightning strikes, the charge of the ground directly beneath the thundercloud will become what? Connor, you asked a question yesterday, I think, about the hair on your arm standing up before you get struck by lightning, right? You could change this question around to say, the charge of Connor's arm hair directly beneath the thundercloud will become, what's the answer to that? Positive by induction. The answer would be A. Induction because charge isn't actually transferring. Positive because, well, negative right here, this is the Earth that's neutral. The negatives get pushed away, leaving, I mean, the Earth is still going to be neutral, but the part that's closest to the cloud will become positive, opposite. Right? 38. It says, during the downward lightning strike, the charge on the top of the tree becomes, during the time these electrons from the cloud are going down to the ground, the top of the tree becomes, who says negative? Who says positive? Yeah, it's negative And it's negative by, what is it? Conduction, because you're transferring charge from the cloud to the ground. All right? Negative by conduction. The answer would be B for that one. All right, here's another one. See what we can do with number 36, please, in your worksheet booklet. Okay, what do we got? It says a student places a positively charged sphere near a metal rod. Both are on insulated stands, and the rod is grounded. They're talking about insulated stands here just to remind us that we don't have to worry about electrons going like this way. It's insulated from the ground, so the only transfer of electrons to the ground is going to occur in this grounding wire here. So we want to know the distribution of the charge on the rod. Well, let's draw some charges. Equal number of positives and negatives. What happens when I bring this positive object nearby? What's going to happen to the protons in there? They're going to stay where they are. What's going to happen to the electrons? They're going to move where? To the left. Good. They move to the left. Not necessarily all of them, right? But lots of them move to the left, leaving end X negative. Now, we're also going to get the electrons moving up from the ground, right? So in the end, the whole thing is going to be negative. Distribution of the charge is negative at end X, and the electrons would move onto the rod from the ground. The answer is going to be D. How many people said D for that one? Good. What else did people say, though? How many people said B? A? C? All right. I want to show you one more quick thing, and this is our little demonstration, but we got enough of these actually to use to actually do it, all of us to do it, but it doesn't work very well, so it's probably not going to, what I'm about to try to show you right now probably isn't going to work very well at all, so just bear with me. Just pretend that it works. I'll tell you what's supposed to happen. This is called an electroscope. This electroscope looks more or less like the two electroscopes you see on the board here, not exactly the same. Both of these consist of a metal ball up here with a metal rod, and on the end of that metal rod are two really, really thin, really, really light pieces of foil, of metallic foil. It's kind of like tin foil, like aluminum foil you have in your house, except not nearly as thick and heavy, much, much thinner. You've ever seen gold foil? You see it in a baking section. Gold foil, it's like that, okay, kind of thickness. Anyways, this one's the same thing, except this was this is inside an Erlenmeyer Flask. The one that we have here in the classroom, almost the same thing, except that it's two pith balls coated with a metallic coating on the top of it. Why do we use this pith ball? Pith ball is a material from the inside of a plant, and we coat it with a metal, with a metallic paint, and works really, really well in electrostatic experiments because now it's a conductor and it's really, really light. Okay, very, very light, just like the foil is. Now, what happens if I bring a negatively charged rod nearby the electroscope, like this? Take my piece of dead rabbit here, and I rub it on this neutral rod. The rod becomes negatively charged. You can hear it, right? Connor said he could see a little bit of rabbit fur sticking to it before. You can hear it if I bring it nearby even. When I bring this nearby, the pith balls should spread apart. It probably won't. You see them moving a tiny bit. Can you see that? Tiny bit of movement, but it's not doing anywhere close to what it's supposed to do. Pretend they did. Pretend they spread apart there. Hey, look at that. When I bring that negatively charged rod nearby, they spread apart. Why? Why do they spread apart? Well, let's draw this diagram a little bit bigger. Here's the ball of the electroscope. Here's the metal rod that goes down to the leaves. The ball of the electroscope is neutral. So is the rod of the electroscope, and so is each of the leaves of the electroscope. The leaves stay together here now because gravity pulls them together. But if I bring that negatively charged rod nearby, what happens to the protons in that electroscope? Stay where they are. What happens to the electrons? They're going to be pushed down. So now we're going to see these negatives, not all of them, but I'll draw all of them just to exaggerate it. You're going to see them all going down here. I guess we'd have 2 and 2, and no, one side would have 3. We have a total of 5 negatives, and we have a total of 5 positives. You can see that both of these leaves both become negative. What happens is they both become negative. Stefan? What happens is they both become negative, Jesse? Yeah, they're going to repel each other. So now we got 2 leaves that are negatively charged, and because like charges repel each other, these guys are going to repel each other. It's going to look like this. What's going to happen if I switch this to a positively charged rod nearby? Well, this time the negatives are all going to be pulled up, right? Same number of negatives, same number of positives. But now the ball of the electroscope becomes negatively charged, and the leaves both become positive. Positive and positive will repel each other. The leaves still will be spread apart, but they're spread apart because of 2 positives as opposed to 2 negatives. This electroscope doesn't tell us how much charge we have. It doesn't measure charge. It just detects charge. It tells us whether we have charge present or not. That's it. Now, how would we change this to make it permanent? Attach a ground wire. It doesn't matter where we attach the ground wire. You guys learned earlier on that the position of the ground wire is irrelevant. What's going to happen here? Well, in this case, electrons will be pulled up. You're going to get a bunch more electrons in here. And at some point, the ball of this electroscope won't be able to hold them all. So some of them are going to filter their way down here. Now the leaves will be spread apart, not because they're both positive, but because they're both negative. If I cut that ground wire, then they're pretty much stuck, right? And it remains negatively charged, and they remain spread apart. Now, eventually, the charges will leak off into the air, because air is not a complete insulator, but not really permanent, but it's going to stay that way for a little while at least. Yep. So we'll get some questions on page 523. I want you to do on 523, number 8, 9, and 10. And I'll give you a little bit of time to work on those right now.